Please welcome Juergen Schmidhuber.
Three prisoners were sentenced to death, one of them French, one of them German, one of them American. What is your last wish? They ask the French guy. He says, one exquisite bottle of exquisite French wine. What is your last wish? They ask the German guy. He says, I want to give a speech. What is your last wish? They ask the American guy. He says, I want to get shot before the German starts his speech. Unfortunately for you guys, it is too late now. This is my name. This is how to pronounce my name. I'm affiliated with the ITSIA, the Swiss AI Lab in Lugano, and I also have a group at the Technische Universität München. All my slides are designed according to recursive applications of the harmonic proportion, the golden ratio, and that makes them very compressible, and therefore has a lot to do with my talk, because it's all about compression and compression progress. Any understanding of intelligence would be incomplete without an understanding of things such as art and science and music and humor. I will show that there's a very simple algorithmic principle that can explain these things. It's so simple that it fits on a single slide. What should an unsupervised intelligent agent, be it a human baby or an artificial agent, what should it do? How should it deal with the data that is streaming in through the input sensors in response to the actions that it's executing? You have to find regularities in this history of inputs and actions that you store, and in other words, you have to compress it. You have to compress the history. Whenever there's a regularity, a symmetry, or whatever, then you can write a program that needs less bits than the raw data and still encodes the entire data. So that's what compression is about. Now let's define the simplicity or the subjective compressibility or the subjective beauty of some data point x given some subjective observer O at a given point in his life t. And that is just the number of bits you need to encode the incoming data, the x, at this point in time with the given limited compression algorithm that you have. For example, most of you know a lot about human faces. You saw so many of these faces, and now you are carrying around with you some sort of prototype face, which allows you to encode new faces in the visual field by just encoding the deviations from the prototype. A new face comes along, and it looks very much like the prototype face, then you just need a few extra bits to store that new face. Your lazy brain likes that, because it doesn't want to waste a lot of storage space. The more the face looks like the prototype face, the fewer bits you need to encode it, and the prettier, in a certain sense, you find it. This is just a word. We just count the bits that we need to store the new incoming data. For example, a face that is very regular doesn't need a lot of bits to be encoded. I tried to come up with a very simple geometric description of human faces. It takes a long time to come up with any geometric scheme that makes sense at all. This face, of course, is interesting only as long as the symmetries, etc., are not yet known, but then it becomes boring. The important thing is not the compression by itself, but the first derivative of the compressibility, because what's really going on is that as new data is coming in, your compression algorithm improves all the time and becomes a better predictor of the data. Whatever you can predict, you can compress, because you don't have to store extra what you can predict. So prediction and compression are almost the same thing. And to the extent that your learning algorithm is improving the predictor, such that it becomes a better predictor on the observed data so far, you are saving bits. There's a novel pattern in the input stream where you still have some learning progress. Whenever you save a few bits, that's an internal reward signal, an intrinsic motivation, an internal joy signal, and that's what you want to maximize for the future. You want your controller that is directing your arms and your actuators to move such that you get additional data from the environment where your particular compression algorithm still can make this type of progress. And there are many reward maximizing algorithms and reinforcement learning algorithms that in principle can do this. Creativity and curiosity, just the same aspects of the same principle, trying to make new data, more data, which is compressible in previously unknown ways. Again, in discrete time, the formulation without derivatives, if you don't like that. The simplicity or compressibility, or beauty if you want, of the data is the number of bits you need to encode it, given what you already know about the data. The interestingness of the data is the change in the number of bits. So you get the data, you learn a little bit on it, which means you can now compress it a little bit better, and that's your internal reward signal, because you have a novel pattern which you didn't know yet. And that's why you find it interesting. Let me give you an example, a very simple example of a robot sitting in a dark room. The input doesn't change. It sits there, and no matter what it does, it's always black, black, black. So it's extremely compressible input. But because it already can predict that very easily, because you just can predict by saying the next frame is exactly like the previous one, you can totally compress the input, and it's totally boring because there is no compression progress, because you don't see a pattern that you didn't already know. Now let me give you another extreme example, which is just the opposite. Suppose you're sitting in front of a screen with white noise, and there are all these black and white pixels coming with equal probability at you, conveying maximum traditional Shannon information or Boltzmann information, and still this stream of inputs is totally boring again, because yes, it's very uncompressible, you cannot find a short pattern, and you cannot improve your current description of the signal, which again means that there is no compression progress. So this is also boring. The only thing that is interesting is stuff like certain types of music which you didn't know yet, but which is maybe a little bit similar to what you already knew about music, and whether there's a new little harmony in there which you haven't heard just in this way, and there you have a little pattern where you save a couple of bits, and that's what motivates you to listen to the same song again. Discovery in physics, for example, is just a very large compression improvement. Suppose you have 1 million videos of falling apples, and they all fall in the same way. It's always the same way they fall down. You can extract the rule behind this behavior, and it turns out that it's a very simple program that describes gravity, essentially, that you can use again and again for all these many different videos of falling apples to greatly compress these orange blobs that are falling down there. You cannot compress everything. There are random fluctuations and noise and whatever that you can compress, but there's a substantial aspect of the incoming data that you can compress. And there you can make a lot of compression progress, suddenly save a lot of bits. But the same is true also in the arts. Suppose there's a guy who figured out a way of drawing Obama with just 5 lines, such that everybody says, hey, that's Obama. So you have an artist who somehow extracted the essence of the face, such that you have the same impression as you're looking at this face that you get when you are looking at a high-resolution photograph with 1 million pixels. So somehow there was a compression progress in the artist, as he was trying many times to come up with a convincing caricature, and there is a similar thing happening in the observer when he sees that for the first time. So the scientists and the artists have something in common. They always try to make new data which is compressible in a new, previously unknown way. A new pattern, a novel pattern means, yes, it's compressible, but in a way that I didn't know yet, such that my compressor can make this learning progress and can save a couple of bits. You know, before I came here, I thought this is going to be just another Singularity Summit, and probably there won't be much of an audience, but you are actually a large audience by my standards. The other day I gave a talk and there was just a single person in the audience. A young lady. I said, young lady, it's very embarrassing. but apparently today I'm going to give this talk just for you. And she said, okay, but please hurry, I gotta clean up here. We had a whole bunch of different implementations of the principle that I just explained. We didn't start that yesterday. In 1990, the first systems of this type were implemented using very simple prediction machines, artificial neural networks. Recently, two guys in California, they took the 1995 model and found that it explains eye movements of humans better than previous models. Let me give you another example of very compactly encoding images. Let me start with a bunch of large circles. We add 4 times as many circles with half the size. We add 16 times as many circles with 1/4 the size, and so on. And now the rule is I can create new drawings, but only by using arcs that are on these legal circles that I get there. And there are a few large circles and many small circles. Now I can encode drawings like this one by enumerating all the circles, for example, giving each of them a little number. The large ones get small numbers, the small ones get larger and larger numbers. And then you can very compactly encode drawings like this one. Here I'm removing all the green circles, which I'm not using, and leave only the red circles, which are the only ones that I need to specify the details of the drawing. And finally, I get a very simple drawing that can be encoded by very few bits of information, just a few lines of code, much more compressible than, for example, a JPEG encoding of the same image or a GIF encoding. And that would be then an example of low complexity art, which I defined in 1997 in a journal which is dedicated to such things. Leonardo is the journal. And let me give you another example. Again, the same scheme, which can be used to very compactly encode drawings that follow these basic rules. And here we see a self-similar femme fractale. I'm removing all the circles that I'm not using, and then only the green circles are left, which are the only ones I need to specify the details of this drawing. And then finally, we have again an image, a low complexity artwork that can be encoded by very, very few bits of information. What is next in artificial creativity and artificial curiosity? Well, our first implementations, they use these feed-forward networks. Devices that learn to map an input to an output. But now we are much more focused on these recurrent neural networks, mapping arbitrary input sequences to arbitrary output sequences. Currently, the best connected handwriting systems are using recurrent networks like this. Robots designed to work in surgery settings learn to tie knots using recurrent neural networks. Once you've got these recurrent networks, which are just supervised compressors of the data history, then you have to look at what happens to these reward signals that you get as you are getting a better compression. And then these reward signals, they go to the reward optimizers. We often use certain novel techniques for coevolution. We see a little robot which has learned to balance a pole. Maybe you see that. It has 3 wheels. It's controlled by, again, a recurrent neural network. But now there's no teacher that tells the robot what to do. In the beginning, the pole always fell down. But then after some time, it maximized trial length and became better and better. But then it was starting to run against the wall all the time. And finally, it learned to use its sensors without a teacher. Down here, we see the same robot, but now with 2 poles on top of each other. So now here there's a joint in between, and this robot, after 4,000 iterations, trials, has learned to balance another pole on top of the first one. Here you see that. Here there is an object which is moving through water, and then it's generating turbulence. Now what you want to do is you place little tiny actuators on top of this object such that they create little tiny anti-turbulences which kill the vortices, such that you can reduce the drag of the object. Here you see a supercomputer simulation of the vortices in the back, and down there here we see what happens before the learned behavior is switched on, and suddenly you will see that these vortices get really small because the system has learned to generate anti-turbulence, again through one of these reward optimizing algorithms. The drag goes down to 40% of the original value, which was an excellent result a couple of years ago. And we are currently implementing in a more complex system these principles on a humanoid like this. Markus Hutter, a couple of years ago, did a postdoc in my lab in Switzerland, and he came up with this algorithm that every computer scientist should know, a universal problem-solving algorithm which takes any well-defined problem as an input and computes the solution to this problem as quickly as the fastest unknown algorithm for solving that type of problem, that provably solves that type of problem. It's as fast as the fastest method, except for an additive constant that disappears as the problems get larger and larger. As, for example, you are trying to solve a traveling salesman problem, and the number of cities gets larger and larger, this additive constant becomes negligible. Most problems are solved because almost all problems are large problems, and there are just a few small problems. In this universe, these constants still are relevant because the problems are so small. Now, can you do anything about these constants? Yes, you can use an old trick of Kurt Gödel, who in 1931 founded theoretical computer science, used the integers as a universal programming language to create formulas that talk about themselves, that are self-referential, and they say things such as, I am not provable by a computational theorem proving procedure. And in this way, he showed that math is either fundamentally flawed or contains statements that are true but not provable. And he was an Austrian. He did this work in Vienna, but later he came to the United States, just like another great Austrian thinker who then became governor of California. And we can use the self-reference trick of Gödel to build another type of optimal universal problem solver, which is totally self-referential in the sense that it can inspect any of its code and can rewrite any of its code, provided that it first can show, through a proof, that the rewrite is good according to some user-defined utility function, which can be anything. Any problem can be written, if it is well-defined, as a utility function. This is a rather novel application of Gödel's self-reference trick, which can be used to build a universal problem solver, which is theoretically optimal in a certain sense. Here I just want to point out that we are currently entering, through results like that, into a phase where AI, artificial intelligence, is not any longer just a collection of heuristics, but it is becoming a real formal science like probability theory and established sciences like that. And that's good because heuristics come and go, but theorems are for eternity. I want to put all of this now into this historic context. Wilhelm Schickard, he built the first computer. Babbage came along in England. 2 centuries later, in the 1830s, he came up with this idea of having a program-controlled computer. At least the idea was there. And then we had to wait only 100 more years, 1 century later, and modern computer science started. Because this guy here, Konrad Zuse, he completed the first program-controlled working computer, the World Wide Web, exactly half a century later. Now you see the pattern. We will have an infinitude of additional milestones, and they are going to converge in 2040, which is the omega point. I like omega much better than singularity. Omega, it sounds so much like, oh my God. There's only one problem with lists like that, which is that actually omega should have happened already in 1540. In 1540, Life magazine made a list of the most important events of the millennium. And their number 1 was the invention of the printing press, 1444 by Gutenberg. And the second most important event in the history of the past 1,000 years, according to Time Life magazine, was the discovery of America through Columbus. Columbus did not become famous because he was the first to discover America, but because he was the last to discover America. Number 3, the Reformation, according to Time Life magazine. And you see, there's a pattern, 96 years, and then between these 2 events there are exactly 48 years, and then half of that, 24 years, It's about to converge in 1540, you know? And so, of course, there never has been a shortage of prophets claiming that the end is near. Yes, I really have to go. Okay. All right. Think about that. Thank you very much for your attention.